examples, we might have noticed that the different loads like point loads and uniformly distributed loads are depicted differently on our shear force and bending moment diagrams. This is because different loads are depicted with different types of mathematical functions. These functions can be linear or parabolic or hyperbolic equations. In the next few slides, we will be seeing how each of these loads are depicted. So the first will be point loads. Let us assume that we have a simply supported beam on which two loads are acting. As for the shear force diagram, the point load will be depicted using a linear function where y is equal to shear force value. At the same time, x is equal to the span, basically the span of the beam. Thus, if we look at it mathematically, mathematical equation would look something like this, where y, the shear force, is at some value for the entire span until there is a change in the value. While BMD is also a linear function where y is equal to x, that is shown in the second figure, where we have y value equivalent to the x value, which is the span. This is exactly why in this figure our BMD plot has a tilt in both the areas. This is exactly why our BMD plot has a tilt which is equal in both the regions. The next type of loads that we will be seeing are uniformly distributed loads. The shear force over the span of the beam will reduce as per the intensity of the beam. Thus, for a shear force diagram, the shear force is depicted using the linear functions, and on a graph it would look like this. So basically it would be a line that is tilting where y is equal to x. The span as seen will have a gradual reduction behavior when it comes to shear force. As far as bending moment diagram is concerned, it is basically a parabolic function. Parabolic functions have the following mathematical equation of y equal to x square. Thus, the shape of the curve would be a curve with the function y which is equal to x square as shown in the figure. Thus, for uniformly distributed loads, the shear force would reduce according to the intensity of the load and the bending moment would increase by parabolic function. Next, we will be looking at uniformly varying loads. For a uniformly varying load, the load will vary from an intensity of 0 at one end to maximum at the other. Thus, for the shear force diagram, a parabolic function would be used where y is equal to x square. The curve would thus look something similar to this, while the bending moment diagram would be depicted using a cubic function wherein y is equal to x cube. This function is shown using the second diagram. Next, we will be looking at bending. The definition of bending is to curve out of a straight line or position. That is, it is a movement that causes the formation of a curve. This happens when a load is applied to a straight element which leads to its curving. In this section, we will look at how to calculate and derive the bending formula. Let us look at what happens when a beam is loaded. Here we have a simply supported beam on which there is a point load acting at the midpoint, that is L by 2. L by 2 is half of the span of this beam. The top part of the beam is under compression while the bottom part of the beam is under tension. This is because the top part of the beam is getting compressed or reduced in length while the bottom part of the beam is in extension or elongation. The direction in which the beam will bend depends on the type of load, and in this case, where we have a downward or gravity load, sagging occurs in the beam. Sagging is when the top of the beam sink under a load with a concave curvature. Hogging will occur when an upward or a pulling force is applied to this beam. It will lead to convex curvature. Hogging occurs when there is a reactionary force or pre-stressing is involved. We will learn more about pre-stressing in the upcoming modules, and also we will be calculating and deriving the bending formula to do that. But before that, we need to know what a neutral axis is. So let us assume that a beam is placed under a load. In this case, the beam is under sagging conditions. Thus, the bottom half of the beam is under tension depicted in green, and the top part is under compression, which is depicted in orange. The bottommost part of the beam will be under the highest amount of tension, while the topmost part of the beam will be under the highest compression. Now let us assume a section of the beam, that is one portion of this beam that is subjected to the load. When we plot the cross section of the beam and the stress across the cross section, first is tension, and we know that tension is maximum at the bottom. So if we can see here, the tension is maximum at the bottom and then it keeps reducing until it reaches to one point where the value of tension is 0. The same way, if we take the highest compression value, when we go down the y-axis, the compression value travels till it reaches the tension region, and when it reaches this point, again the compression value will also be reduced to 0. This point where both compressive force, which is Fc, and tensile force, which is Ft, is 0, is called as the neutral axis. Thus, the neutral axis is the axis where stress is 0. If we have to draw the neutral axis across the beam, then this is where it will be. Now, let us take a simply supported beam. In this beam, we will take a section AB that experiences pure bending in the tension zone. This section is at a distance y from the neutral axis. When this beam is placed under load, this section will bend, and in this case, the bending radius will be r, and theta is the angle of bending. We can call the bend section as A dash and B dash, while y dash is the distance of deflection or bending, that is from the neutral axis. Here, the value of theta is very small in reality and it will tend to 0. Now, let us look at the original unbent section of AB. The original length AB will be equal to r theta. This is derived as follows. Cos theta, which is adjacent by height, is equal to r by AB. That is the radius of the bend section divided by the original length AB. Theta tends to 0, which is in reality. We can say that theta is a very small value and cos theta as a very small value is equal to 1. Thus, AB is equal to r theta. Now, let us look at the bend section. The bend section is A dash B dash. This will be equal to r plus y into theta. Again, this is because we know that cos theta is equal to 1. So, A dash B dash will be equal to r plus y into theta. Next, when we look at the strain in the section A dash B dash, epsilon will be equal to delta L divided by L naught, wherein delta L is the change in length and L naught is the original length. The change in length is the difference between the final length and the original length. Here we know that the final length is r plus y theta and the original length is r theta. So from that we can calculate r plus y theta minus r theta divided by r theta. So from calculations we will get epsilon value as y by r, wherein y is the distance from the neutral axis to the bend section, which is A dash B dash. Next, when we take stress in A dash B dash, it's sigma equal to F. Next, when we take Young's modulus, E is equal to epsilon divided by sigma. We know that epsilon is y by r and sigma is F. So from that, E will be equal to y by r divided by F. Thus, to derive the simple bending equation, E by r is equal to F by y, where E is the Young's modulus, r is the radius of bending, F is the stress in the element, and y is the deflection in the element. Let us now see what moment of resistance is. Moment of resistance is when this beam is placed under a load. When this beam is placed under a load, it is under both tension and compression. This forms a couple across any cross section which has a moment. The compressive force Fc generates an anti-clockwise moment mc, while the tension force Ft generates a clockwise moment mt. The moment of resistance within this section is equal to the net bending moment, that is equal to mc, which is the compressive moment, plus mt, which is the tensile moment. So here we can see that mr is equal to net bending moment, which is equal to mc plus mt. Now, assuming that we have a very small area which is depicted by del A, this area is at a distance of y from the neutral axis in the compressive zone. The stress on this element can be given as F, which is equal to E by R into Y. Now, this value is something which we have got from the bending equation. Next, the force on this element will be equal to stress multiplied by area. We know that force is equal to stress multiplied by area, and we got the stress here, which is E by R into Y into the area del A. As we've seen the force on the element, next we'll see moment about the line NA. Now this is also from the element. From the element is in a distance of y from the line NA. And if we have to find the moment, we know that the formula for moment is force into distance. We know that force is E by R into Y into del A, and the distance here is y. So finally we get a moment of E by R into del A into y square. Next, for the moment of resistance can be given as the sum of all moments on the element. So right now we can say that sum of all the compressive moments on the element, because this moment is on the compressive side. Now moment of resistance is equal to the summation of E by R y square del A. Here we know that E by R is a constant. So placing E by R left of the summation, we can call y square del A as I, or the moment of inertia. We can call sigma y square del A as I. We can denote sigma y square del A as I, which is moment of inertia. So basically moment of inertia will be equal to the summation of y square del A. Finally, from whatever we have derived earlier, the moment of resistance equation will be m divided by I, which will be equal to E by R, wherein m is the moment of resistance, I is the moment of inertia, E is the modulus of elasticity, and R is the radius. This moment of resistance equation is also called as Bernoulli's bending equation. So the Bernoulli-Euler bending equation is the relationship between the bending moment, moment of inertia, elastic modulus, and radius of bending, stress, and distance of element from the neutral axis. From the earlier equations, when we take all these into account, our Bernoulli-Euler bending equation will be m by I, which equal to E by R equal to F by Y. Next, we look at section modulus. We know that m by I is equal to F by Y. We got this from the Bernoulli equation. Thus, F, or the stress in the element, is equal to the moment of resistance divided by the moment of inertia multiplied by Y, which is deflection. Maximum stress in this element will occur at the end. That is when Y is at its maximum limit. Thus, F max will be equal to m by I Y max. M is equal to I divided by Y max. This we have seen in the previous equations. So, by substituting these values inside the F max equation, we'll get F max is equal to Z into F max, where Z is the section modulus. Thus, section modulus is equal to the moment of inertia of cross section about the neutral axis divided by the maximum distance from the neutral axis, that is Z is equal to I by Y max. So basically, section modulus is used to calculate the safe moment of resistance for a specific material. The next section will be deflection. Deflection is the measure of how much a beam will bend under a load. Let us assume that we have a cantilever beam with a point load at its end. This beam will bend downwards as shown in the figure. The dotted line shows the curvature of bending that will occur in the beam. Deflection can be expressed in two ways. First is using angle of deflection, that is the angle at which the deflection curve is with respect to the original element. It can also be expressed using distance, where the endpoints of the beam and the distance between them after curvature and before curvature, which is delta deflection, is a crucial part. It can also be expressed using distance, the endpoints of the beam and the distance between them after curvature and before curvature. This can also be given as delta. Deflection is a crucial part of engineering design because too much deflection is an indication of failure. Now, what is flexural rigidity? The moment equation is m by I, which is equal to E by R, and that is equal to F by Y. Let's look at the radius of curvature of beam, which is equal to EI divided by M. Now, EI, which is the multiplication of Young's modulus and the moment of inertia. This is called the flexural rigidity of the element. Now, flexural rigidity gives us a measure of how stiff the material is against flexural bending or curving. In the next few slides, we will calculate the amount of deflection or bending in a curve. We will derive the deflection formula. To do that, let us assume a fixed beam with a point load acting on one end. This beam will curve downwards. This is called the elastic curve of the beam. The slope of this elastic curve is y by x, where y is the vertical axis or the amount of bending and x is the span of the beam or the horizontal axis. Let us assume that the deflection in the beam is negligible. Thus, the radius of bending is as shown. The deflection is delta, which is a very small value since the deflection is negligible. Knowing that, we can now calculate tan theta, which is equal to opposite side dy divided by the adjacent side dx. When we differentiate both these sides, we get d square y divided by dx square, which is equal to secant square theta d theta by dx. So now let us calculate the Euler-Bernoulli deflection equation. From the figure, cos d theta is equal to r by ds, which is adjacent divided by opposite side. Since d theta is a negligible value, cos d theta is almost equal to d theta. Thus, 1 by r is equal to d theta divided by ds. And when we take differentiation, it is equal to d square y divided by dx square into 1 by secant square theta. We know that secant theta is dx secant square theta. After differentiation, it is equal to d square s divided by dx square, which is approximately equal to 1. Therefore, 1 by r is equal to d square y divided by dx square, as we know that secant theta is approximately equal to 1. Now, if we look at the bending equation, m by I equal to E by R equal to F by Y, it can be rewritten as m, which is the moment of resistance, which is equal to Young's modulus multiplied by moment of inertia multiplied by 1 by R, which is the value of bending. Thus, moment of resistance is equal to E into I d square y divided by dx square. Since 1 by r is equal to d square y divided by dx square, now using this equation, we can calculate the deflection. From whatever we saw previously, deflection is depicted using delta. Deflection can be calculated by double integrating the previous equation. The equation E I d square y divided by dx square is equal to m can be integrated once. The first integration will give us the slope of the elastic curve, also known as dy by dx. First integration gives us integral m plus c1, where c1 is the integration constant. If we integrate this equation, we will get ei into y, which is equal to double integral m plus c1x plus c2. C2 is the other integration constant. Thus, y, which is equal to the deflection, is equal to double integral of m plus c1x plus c2 divided by ei. Here, m is the moment of resistance, c1 and c2 are the integration constants, x is the distance at which the deflection is measured, and e is the elastic modulus. We can also see that I is the moment of inertia in this equation. Now, using this equation, we can easily calculate the deflection delta at the distance x.